Good morning. Any questions or any comments? I'll start talking about the last topic in this chapter, which is called scaling theory of conductance. So we have like a good reasons to believe that there will be like a kind of Anderson transition, and we also like have seen that the detail of this transition or if, its existence depends on dimensionality, whether you are in 1D, 2D or 3D. But like at this moment we are going to like give like a universal argument about the existence of localization, and it's going to tie up everything we said so far, and this will be the end of this chapter. So classical theory, and what I mean here is like Boltzmann transport. It gives you the so-called conductivity, sigma conductivity, and this is like a local a quantity, and local means for every point there is like an electric field and there will be a corresponding current at that point, and it is going to determine the conductivity. And the conductance, which we use G, is more like a system shape and size dependent, like something like sigma times A over L. This is the one we know from freshman physics. And in general dimensionality, this is going to go like sigma. So A is L to the D minus 1. There's another D here. So this is going to be L to the D minus 2. Like in quantum theory, like quantum mechanically, we have seen G, conductance, not conductivity, is a good quantity. So G is a good object to calculate and analyze. And the reason for this is like if you think about, for example, Landauer, like Landauer conductance, electrons are delocalized wave that propagates in the entire sample, and these delocalized waves can interfere and change this ohmic conductance, and that means this conductance is non-local, and it depends on size, right? Size dependent. Okay, now let's consider these things a little bit more carefully and see what we can get about quantum mechanics. Like quantum mechanics is about electron spectrum, energies, eigenvalues, and energy gaps. So I want to take this quantity or like some form of it, and then express it in terms of spectral properties. So let's consider G, sigma times L to the D minus 2, and let's also consider Einstein relation. Sigma is equal to E squared D n d mu. So this is what we derived previously. Then this G, okay, from here G is going to be, yes, I'll just substitute this here and then see what it gives me. Like, let's do that. So this is E squared D n d mu times L to the D minus 2. So what I want to do here is, okay, previously we had like some scales, like for example, we had escape time, which is also sometimes called like tallest time, was equal to L squared over D. And this is what I want to do here. So let me put one of the L's here, like color. So this is L squared, and now I can erase this. And here this N and this L to D is volume. I want to combine these two, so let me write it like this. So this L to the D is volume and N. And so this is the total number of electrons at a given energy. And I want to write this in terms of, because in the Landauer, if you remember, there was like 2 here. To write it like that, I want to include 1 over 2 there, and this is going to be density of electrons at a given energy per spin. So then let's do this. So this is going to be this object, L squared. I'll use this. Let me define this delta t. This is exactly, let me also define delta t here, delta t, which is equal to L squared over D. This is what we called tallest time. And the second one, so this thing, let's also take this separately. So this is D over D mu at 1 over 2 N LD, but this is going to be D over D mu N of E, that's like number of electrons at a given energy E. And this is, of course, I can write it like this, D E, and this is at E Fermi, E is equal to mu. And I'll write this as 1 over delta E. So if you want, I can just think about, so delta E is going to be something like E over N, right? And in the differential form, this is like a more meaningful quantity. This is like typical energy level spacing. So this one is energy level spacing. Good. And at the end, what we have for G is 2E squared. And here I want to use, for tallest time, I can use the energy time uncertainty to define an energy. Let me call it like E tallest is going to be equal to H over this delta T. And this entire thing is going to be, did I get that right? And this is going to be H D over L squared. Okay, I think that's good. So then the entire thing is going to be this tallest energy divided by delta E.
I missed the part where you just neglected 1 or 2 in the parentheses.
So I didn't neglect it. I said this is like a total number of energies at a given total number of electrons at a given energy per spin. Because it was the total thing. To get per spin, I put 1/2 and I get the 2 out. Why did I get 2 out? Because this is the one in the Landauer formula, and I think I need to have like E squared over H here. So this is E squared over H. Then from here, I can like write this G, which is going to be size dependent because as we know from numerics, spectrum is size dependent and the gaps are going to be size dependent. We can define this so-called dimensionless conductance as these E tau s divided by delta E. And this is dimensionless conductance. And actually, let me take this box to here. So we derive this from the Einstein relation, but this is an Einstein relation is like a seemingly a classical result that comes from like a Boltzmann transport. But this actually is actually more general than that. So this G of L is equal to E tau s over delta E is more generally applicable even beyond like diffusive conductors. Like let me try to explain what this quantity does in like good metals. Like then the question is, what does this quantity do like in good metals and in insulators, right? Let's consider good metal. In a good metal, this G, good metal is like a very good conductor. Then this dimensionless conductance should be something much larger than 1. That means E tau s should be much bigger than energy level spacing. And this means there is like some spectrum, like something like that, maybe. And there is like a typical energy level spacing, which is delta E, but also this E tau s is going to be like, diffusion is about like the broadening of levels, right? Like if I look at this axis like this, it's going to be some kind of broadening here, another broadening here, and another broadening there. So what this means is like spectrum is kind of blurred and it's like continuous, so that electron can just propagate from level to level. It can get into conductor, just jump from level to level and get out of the conductor and give rise to a good metallic conduction. The other limit is good insulator, or like insulating limit. It's going to be G much less than 1, and that means E tau s should be much smaller than delta E. Then exactly the same picture, but this time these levels are going to be sharp like this. Okay, let me just put, so it's going to be like sharp and their overlap is going to be negligible, right? So these are like well separated energies that do not speak to each other, and if your electron ends up being in one of them, it's going to be trapped in one on that one, and it's not going to give any conduction.
Where is ET place? E tau s?
E tau s, so we define it in terms of first from D over L squared, right? It is like there is like some sample size, and I'm looking at the, previously we called it T escape time, but Gerwin Young calls it delta T in that section, so I also call it delta T. And from delta T, that's L squared over D, I formed an energy scale by using energy time uncertainty.
Where did you use that in good metal or in good insulation?
So here, this is the G of L, and I know G of L should be large for good metal. If G of L is large, that means ET should be much bigger than delta E. And I look at this, and what does this mean? It means there are like levels, and there's like some level spacing, and this ET is like energy uncertainty. Uncertainty is large, then these energies blur and mash up together. While on the other limits, insulator means G should be small. If G is small, ET is much smaller than delta E, and these energies are isolated energies that do not speak to each other. So a lot of words, but this argument came from Thales, and I think it's like a very good argument to know. Another thing to notice here is like because in a metal, like there is like these levels kind of overlap, and also like corresponding eigenstates are delocalized, that means these different states can hybridize, and if these different states hybridize, they are going to be correlated. And in metal, energy levels are correlated, and there is like some kind of like a level repulsion, because generally in quantum mechanics we diagonalize eigenvalues, right? Matrices, and find eigenvalues, and generally they do not cross. And from here we kind of expect some kind of spectral rigidity. Like if you like move one of the levels, the other levels are going to respond because of this level repulsion. Whereas in insulator, energy levels are uncorrelated. Or we can say it's like Poisson distribution. And from here, people generally get into like so-called random matrix theory, and then there's like very nice properties of random matrix theory. A theorist really likes to study, and they seem to be quite relevant for real materials. But I'm not going to do that. So then the question is, in general, how do we? So in general, we have like finite samples, right? At least in theory, we are like we have like a finite number of sites, and we diagonalize the corresponding matrix, and we look at the eigenvalues, and they are like certain values, right? How do we determine G of L in real materials? How to determine G of L in, let's call, numerics. And Taules said, okay, let's take one random realization of size L, like this is one sample. And we can basically, right, it is like a small size, we can like study in the computer, so we can do everything about this. But Taules said, let's just repeat this many times. So I'm taking exactly the same block and repeat it many times. And each block here, so each block is same disorder. Then that means h of x is going to be, if the size of the block is x, is going to be exactly equal to h of x plus L. And this is exactly what we had for Bloch theorem. And that means psi of x at any moment is going to be equal to some phase, let's call it e to the I k L, psi, okay, let me write it the other way. So psi of x plus L is going to be like this, psi of x. Then if you have the levels in like a given sample like this, when you like tile the entire sample with many copies, what you are going to have is actually some of these level broadenings, right? Like these bands, just like we had in the Bloch case. And the broadening in each level, like for example this level, is going to be broadened by amount E tau-less, and we can find E tau-less by just using the Bloch theorem. So E tau-less here is going to be, let's say this is the ith level, E I at KL is equal to pi, that's the Brillouin zone boundary, minus E I at KL is equal to 0, that's the Brillouin zone center, and it's going to give you the broadening of each level. Then what we can do is like we can like use periodic boundary conditions, like psi of x is equal to psi of x plus L, and find this thing, the other one, so this one, because in this case KL is going to be 0, so KL is going to be 0, or we can use anti-periodic boundary conditions. Psi of x is equal to minus psi of x plus L, and this is going to correspond to this, and by looking at their difference we can find the towless energy. At least this is what from here determine, let me call it G towless, which depends on L, is going to be this E towless you determined from here divided by typical energy level spacing. And this is what we call towless conductance. Lastly, to relate this G towless to the G we defined earlier, towless set in this configuration, let me just copy this. In this configuration, this is like a 1D, geometry, and from Landauer formula we know what G is supposed to be. G is supposed to be 2E squared over H times N, and N is number of channels in each block, if you want the number of levels in each block. And if you remember, we had like something like T, then there is like impurities, but in this case T is equal to 1 because this is like perfectly periodic 1D sample, no scattering, there is like perfect Bloch waves, and number of channels, right? Number of channels at a given energy N is going to be your level broadening E towless divided by delta E at the given Fermi energy. So this is number of states crossing Fermi level, and this also justifies, right, this N, which is this object, is going to be G towless, which is this object, and this is exactly mapped to G, which we defined here in terms of dimensionless conductance. So then G of L is going to map to G towless, which is like spectral property. Good. And now we can speak about scaling. So in the scaling problem, suppose we have this dimensionless conductance G of L given. Can we use only G of L and nothing else to find G of 2L? Okay, so that's the problem. Like in 1D, for example, we are going to have these blocks, something like that. Let's actually do for the 2 blocks. For this is like for 1D. So this one is going to be for 2D, and in 3D we are going to have exactly the same thing, but it's going to be like broadened, like in 3 blocks. Okay. So there's like 2D blocks glued, and we want to find this G2L in that case. So the towless argument was like, let's think about Hamiltonian of this system, right? There's like a system 1 and system 2, and when you put them, now we are thinking about, like, so different disorders, different disorder realization. In this case, towless argument was like total Hamiltonian H is something like H1 plus H2 plus some tunneling between these two, and we can take tunneling to be a perturbation, And when you take tunneling to be perturbation, we can write energy levels, like each level, for example, En of new system is going to be En of 1 plus En of 2, energy level of first one, energy level of second one. Actually, there will be no first order correction because of like tunneling, and the second order is going to be something like this, right? M not equal to N. There is like this M HT N squared divided by something like EM minus En. Actually, let me call this this total object En0, and this is going to be EM0, EM0. And what we see, and higher order terms, and higher order terms also have the exactly same structure. And we can also write down exactly the same thing for psi, dot, dot, dot. The key observation made by Thales is like, in this perturbative limit, the new energies and new wave functions are also only a function of this delta E, which is the denominator. So this is typical energy spacing delta E, and typical coupling, which is here. So the typical coupling here is going to be given by uncertainty, and uncertainty relation tells us it's going to be proportional to E tau, Thales.
This is the second order correction.
Yes.
What about the first order correction?
So first order is 0 because if you have N H tunneling N, right? So what happens is like an electron goes from here to other side. So and there's no matrix element, right? Because there's like, if you want, there's like a hopping and beginning state. So beginning, so here the beginning state and final state is exactly the same number of electrons in the same block, but there's like a tunneling in between them, right? Tunnel, if you want, tunneling is going to put it like to something like N prime, where one of the electrons hopped on the other side, but the state in which electron hopped on the other side is going to be distinct from the one which it didn't hop. But that's why I trivially just got rid of the first order. Second order and higher terms are going to be in the perturbative series. But this detail is not important. The key about here is like, whatever the perturbation expansion is going to be only, so E of N is going to be only a function of E Thales delta E and nothing else. And if the and also the wave functions are going to be only a function of this E Thales divided by ET, and if wave functions and corresponding eigenvalues are only E Thales over E delta E dependent, everything else also only depends on E Thales over delta E. Of course, this is like hard, so in the perturbative limit, this is like easy to see, but we are also claiming, conjecturing this to be true, even in the non-perturbative limit, which makes sense. Then, here is the scaling hypothesis. So this is the scaling hypothesis. So this G of 2L, which is like a observable of 2 block, or like a 2 to the D block sample, is going to be a functional of this E Thales of L size system divided by delta E of L size system, and it is going to be only a function of this, because this is like dimensionless conductance, F of G of L. So G of 2L depends on G of L and nothing else. That's the scaling hypothesis. And this means if we know G of L at a given scale, we can know G of L in any other scale. Because if I can relate G of L to G of 2L, I can relate G of 2L to G of 4L and so on. And here this F is supposed to be a universal scaling function. What this means, like it only depends on dimensionality and symmetry and nothing else. Good. And typically people do not write the scaling functions like this, because you can also write it like this, but typically they want to write it as like a so-called flow equation or like differential equation. Like if you want, this is like an RG flow equation. And in the RG flow equations, if you ever happen to learn one of these, they are like so-called beta functions, and beta functions are written like this: d ln g divided by d ln system size, right? There is only L here, and typically we make it dimensionless, because this is like a dimensionless equation, and it's going to be given by beta of g only. So this is like a one parameter flow, and the only parameter is g. And we want to understand how g flows as a function of L, the system size. So this is what do we call it? RG beta function. So we want to find this beta function, and we can use different limits to find. Okay, so suppose this is given to you, and we want to like derive beta function for the limit we know what g is. Let's consider a good metal limit, and in a good metal g is logarithmically large, right? It's like a very large quantity, and if g is very large, Ohm's law applies, and in Ohm's law we have this g is equal to sigma times L to the d minus 2. So we derive this, and from here ln g, I can take ln g, there is like ln sigma plus d minus 2 times ln L, and if you want I can also make it dimensionless, but it doesn't matter because I'm going to take, so this thing is going to be proportional to ln g, right? And I want to take this d ln g divided by d ln L, and with the ln L I only have this quantity, and this is going to be d minus 2. So this is one extreme limit, and the other limit is like a good Anderson insulator. And in that case, g is going to be some constant times e to the minus L over some other constant psi, right? In the Anderson insulator, the conductance decreases exponentially with system size because you are localized. From here we can look at ln g is equal to some ln g0 minus L over psi, and d ln g divided by d ln L is going to be, I'll just get rid of this, it's going to be minus 1 over psi d over d ln L. I'm going to write L like e to the ln L, because the derivative is with respect to ln L, and e to the ln L is L, and this thing is going to be minus 1 over psi e to the ln L, and this is minus, and since it is given by this, like ln g over g naught is going to be minus L over psi. This also verifies that our beta function is only a function of ln g. So this is ln g over g naught. So this is Anderson insulator. And once you derive the beta function, the second step in the RG procedure is just look at how things change in the parameter space. So we are considering ln g, and we want to see what beta of g is. And so when ln g is really good, we have like good metal site. And when g is very, very small, that means ln g is going to be negatively large. So this is good insulator site. And in the good metal site, we had this function just a constant. In d here is 3 in 3 dimension, 2 in 2 dimension, and 1 in 1 dimension. Then we can just write this. Let's say this is 1. And if we are in 3D, d minus 2 is going to be 1, and we are going to be starting from here. If we are in 2D, we are going to be starting from here. And if we are in 1D, we are going to be starting from -1, like that. And in the good insulator case, this goes like proportional to ln g, right? And I think there's like did I forget like a minus sign here? I think there's like a minus sign here. In the insulator size, we have something like that. And then it's reasonable to just, right? And the scaling hypothesis says that this beta function doesn't do anything crazy. Like if it doesn't, like it's like monotonous, and it is continuous smooth function. And the only thing you can do with like a function like this is like just to connect these two, right? And we say here, you can see there's like a point where beta function changes sign. And if beta function is positive, okay, here's the definition of beta function. Let's write it here. So if beta function is positive, ln g is going to, because the derivative is positive, if derivative is positive, ln g is going to increase as a function of ln L, or is it going to increase as a function of system size? And we are showing it like this, typically. If you are above G critical, so this is G critical, if you are above G critical, you are just going to go and flow to good metal site. And if you are below G critical, beta function is negative, and you are going to flow towards the good insulating site. And this is the Anderson transition point coming from the scaling hypothesis. And in the red case, the one-dimensional case, we can also like connect these, right? Something like that. And you can see in 1D, you always have like a negative beta function, and there's nothing that can help you. You always flow to good insulate. That's the strong localization in 1D. But lastly, it seems like for blue, d minus, okay, this is d minus 1 is 1, this is d minus 1, 0, this is d minus 1 is minus 1. We don't know if we are going to follow the positive side or negative side, right? And to this order, we cannot tell, and we have to look at beyond this order, beyond this level. And for that, I'm going to consider weak localization. In 2D, and if you remember in 2D, we found like a correction to conductivity, something like, which was minus dt, and return probability to t, and this was equal to proportional to dt 1 over 4 pi dt to the power d. And when we did this thing for 2D, we found it was proportional to system size logarithmically, right? You just take this integral and put like a cutoff, and that cutoff is going to be proportional to ln. We did that there. You can look at those calculations. And in 2D, so this is 2D. That's the one that we need to determine higher order contribution. So d ln g divided by d ln L is equal to, now I want to write it in terms of G because this is a correction to G, so I write it like 1 over G dg d ln L, and this is equivalent to beta function. And if I do this thing on delta G, so d over d ln L on this delta sigma is going to be equal to d over d ln L. Delta sigma is minus ln L, right? That's with some constant. Let's put like a constant a, and this is 1, so this is going to be minus a. Then by comparing with this line, so this is dg 1 over g minus a is equal to beta of g. That right? Sorry, this is times. Then to this order, beta g has minus a over g contribution. To sum up, like in full form, d ln g divided by d ln L is going to be this d minus 2 coming from ohmic formula minus this a over g. In 1D and 3D, this term doesn't matter, right? Because this term dominates both in 1D and 3D. Only in 2D this is important. And there's also like higher order corrections, it's like 1 over g squared and so on. These are much difficult to get. And since we found this to be negative, and it is going to push this blue line to a little bit negative for even for very large values of g, that means it's going to be a good conductor, right? There's no problem, but it's just logarithmically pushed down the negative axis, and it means if you go to really large sizes, it's supposed to just flow to insulating side. And that's the statement of weak localization in the scaling language. Okay, any questions? This is a little bit too much, but I think the difficulty is not technicality. The difficulty is change of jargon, and these people, they speak a little bit different language, and if you ever end up doing these things, you just need to learn the language. It's not some new mathematical technique. Good. All right, thank you.